Okay, welcome to our first lecture in Chem 352. Uh, I'm excited to start the new semester. I wish you were here with me, but that's okay. We'll film 3 lectures, and then on Monday we'll be back in person. We'll start out today with a brief discussion of the syllabus, and then we will go into chapter 16. I know that most of you were in Chem 351M with me last semester, and so if the syllabus part gets boring, you can just fast forward through that part of the video until we start talking about chapter 16. On the other hand, there are some of you who are new to the class, who took 351 from another professor. If I don't go into enough detail for you on the syllabus, if you still have questions on it, please feel free to contact me by email or come by my office for office hours. So first thing, just note the office hours. They are the same as what we had last semester for office hours. So hopefully you can remember that. And please take advantage of those office hours. Last semester, my office hours were underutilized, and so I have plenty of time available for you to come by and seek help on the topics. Yes?
There's a little bit of glare on the screen. Can you turn down the lights a little bit?
Okay. Let's turn that down, and hopefully there's less glare on the screen.
Maybe even a little bit more.
That's as far as it'll go, and be able to see the screen on the board. Okay, we're just adjusting the lights there for a moment to make sure that you can see the screen well. But of course, you can download the syllabus on Learning Suite as well. So we went through chapters 1 through 15 in the Smith Organic Chemistry textbook in 351. We'll be going through the second half of the book, 16 through 29. We'll skip chapter 30 and finish with chapter 31. We're going to do those chapters in order, except we will move up chapter 29. Chapter 29 will help you with an assignment that we will have towards the end of the semester. So we're moving it up to make sure you learn the material in that chapter that will help you with the synthesis assignment. You'll see that we'll have 4 exams. All 4 of those exams are scheduled for the testing center. We're not terminating the in-person instruction this semester like we did last semester. So we'll have 4 exams in the testing center. There will be a mixture of multiple choice and short answer questions. For those of you who were in 351M, the format and length will be identical to the exams from 351M. For those of you who were not, there will be a sample exam posted on Learning Suite, so you'll have an opportunity to gauge the exam and the length of the exam and the format on Learning Suite. And then the final exam, instead of being online like it was in the fall, will be held in person in the classroom at the time scheduled for our classes. The 10 o'clock section will have the final exam on Tuesday, April 20th. The 11 o'clock section 2, will have it at 11 o'clock. So make sure you have these dates and times in your schedules because those are the only times that the final exam will be given, and they will be given in this classroom. So the exams will be worth 100 points each. The final exam is worth 200 points. The remainder of the points come from written quizzes, iClicker quizzes, a synthesis assignment, and a take-home quiz. The synthesis assignment and the take-home quiz will come later in the semester, so we'll talk more about those later on. Let's just talk a little bit about the written quizzes and the iClicker quizzes. So the written quizzes, I'll have to change this. We will announce them this semester. That's because if we don't announce them, and we have a quiz in 10 o'clock, then obviously the 11 o'clock students will find out about it. And so just to eliminate any unfair advantages, we will announce the quizzes. Normally, I don't announce the quizzes because I find it to be a powerful incentive for students to be prepared to come to class if they think that there might be a quiz in class. But unfortunately, we're eliminating that this semester because of the fact that we're teaching the class back to back with reduced numbers in each section in order to allow everyone to be meeting in person. So I'll change that and I'll post a revised version on Learning Suite. The quizzes will be announced. They will be held at the beginning of each class period when we will have them. The quizzes will last about 5 minutes. They'll be short. They're designed to be at the same level as the easier homework problems in the book, the ones that you find embedded within the chapters, as opposed to the medium and challenging problems that you find at the end of each chapter. And so they're essentially designed to make sure that you are keeping up with the reading in the textbook and that you are attending class regularly. Makeup quizzes will only be allowed in the event of COVID quarantines, other illnesses that prevent you from coming to class, family emergencies, or university approved trips. There are very few university approved trips going on right now, so I suspect that you'll be here in class unless you are forced to quarantine or are otherwise ill. So there are 50 points available from quizzes. They're 10 points each. There will be a minimum of 6 and possibly more. In the fall, we had 7 quizzes, which means that you'll be able to drop 1 or possibly more quizzes. In the fall, you were able to drop 2 quizzes. And as I noted in the email I sent you, our first quiz will be on Monday, January 11th, the first day that we're meeting in person, and it will cover the material from these 3 lectures that we are giving, that we're delivering via Learning Suite remotely. So think of it as the summer reading check quiz. If you took AP English or AP History in high school, you typically had summer reading assignments. And usually the first week of school, you would have some sort of a quiz or something like that to check to make sure you did your summer reading. So in this case, the quiz we'll have on Monday is to make sure that you have viewed these videos and you have read the book for chapter 16 and the first 2 sections of chapter 17. So iClicker quizzes, we will have iClicker questions at random points during the lectures. Some class periods will have an iClicker quiz. Some class periods we might have more than one iClicker quiz. Other class periods we won't have any iClicker quizzes. It is your responsibility to make sure that you have an iClicker that has batteries in it and is functional and also registered. And those will start for credit on Monday. We might have some iClicker quizzes during these recorded lectures, and those won't be for credit. Those will just be for practice. But once we start in-person instruction, the iClickers will be for credit. So make sure that you have a functional iClicker and that you have batteries. Like we did last semester, you will be excused from iClicker quizzes only if you are participating in a mandated quarantine, either due to having COVID or being exposed to COVID. So if you are quarantining, make sure you contact me so that I can put your name down on the list as being excused from iClicker questions for those lectures, okay? All right, and then we have homework, which is not listed here in terms of the points available for the class. That's because the homework is worth 6 points. And what we do at the end of the semester when we make the curve for the class and find the breaks between point totals for different letter grades. Any student who is within 6 points of the next available letter grade, we will grade their homework. It's based on percent completion. And what we'll have you do is self-report your results for each chapter for the assigned homework. And those assigned homework problems can be found in a document that is posted on Learning Suite. And we will, if you're within 6 points of the next available letter grade, we will pull out your homework notebook. We will choose a few chapters at random to double check and make sure that what you have reported is accurate. If it is accurate, you will get the score that you self-reported. Of course, if it is not accurate, you will receive a 0. Now, typically, about 10% of the class will end up within 6 points of earning the next higher letter grade. But because the final exam is worth a lot of points, you don't know going into the final if you're going to be on the border. So it benefits all of you to be doing the homework diligently. The homework, as I note here, is also one of the best ways to prepare for the exams. Organic chemistry is a problem-solving discipline. The more practice you have solving problems, the better you will do on exams. Our book has an outstanding set of homework problems. That's one of its strengths. And so I strongly encourage you to work those homework problems. Sadly, what happened in the fall is that the students who ended up on the border, in each case, did not do enough of the homework problems to move up a grade. And I was really disappointed about that. I like to award high grades. I only award the grades that students earn, but it makes me feel good when students have worked hard and earned a grade, and I can award that to you. I was unable to move any students up who were on the borders because those who were on the borders did not complete enough of the homework problems. So I encourage you this semester as a whole to be more diligent in working those homework problems. It'll make a difference both in your preparation for the regular exams and in your final grade if you end up on the border. Okay, we've covered most of the information here on the back page. I'll just highlight a couple of items. One is that there's an online tutorial system known as Bacon that is optional. There's a small fee, I believe it's $6. It's based at UCLA, and it just covers their costs for maintaining their servers and maintaining the system. And there are online tutorials that match up with some of the topics we will be studying this semester. If you register for the Bacon system and you go through those tutorials, which can help you prepare for the regular exams as well as the final exam, then your score, your average on the Bacon tutorials, can replace your lowest quiz score. So it can give you another opportunity to replace a low quiz score in addition to the extra quiz or quizzes that we will have throughout the semester. And then we give an extra credit opportunity. There's a handout on Learning Suite that provides more details on that. But you can make a music video parody with organic chemistry lyrics. And you can, if it's well done, you can earn up to 5 points of extra credit. There weren't very many music videos submitted last semester. I believe that was probably due to the fact that the in-person instruction ended early and you didn't have a chance to get together to come up with music videos. There have been several clever music videos submitted in the past, and there are links to those on Learning Suite if you want to look at them for ideas. I'm hopeful that more students will participate in that extra credit opportunity this semester. Those students who participate typically enjoy it and think that it's a fun opportunity, a fun way to get together in a group and earn some extra credit. And then we have the same TAs, Alex and Preston, that we had last semester. We're privileged to have them continue with us. They will be available in our online tutorial lab, and they will also be setting up online recitations. So they'll be contacting you and looking for times that are good for those online recitations. So that's what we have for as far as the syllabus goes. One thing I will mention is that we're going to cover many more reactions this semester than we did last semester. Last semester, we focused a lot on fundamental concepts and not as much on reactions, although towards the end of the semester, we did have a lot of reactions. This semester, we're going to have a lot of reactions in almost every chapter. And so it's important for you to know how to learn reactions and study reactions. We talked last semester about making flashcards and how that can be helpful, and also about the importance of learning mechanisms. So make sure that you know the mechanisms. If you need help making flashcards to learn reactions, please see me, and I'll be happy to explain to you how to do that. All right, so we'll shift focus now away from the syllabus and now towards chapter 16. So chapter 16 is entitled Conjugation, Resonance, and Dienes. And we're going to hit all three of those topics today. We're going to define conjugation, We're going to have a bit of a review of resonance. Remember, resonance was one of those topics that we covered at the beginning of 351 that I told you we would see throughout the entire year. And so hopefully you remember resonance. We'll have a brief review of that. And then at the end, we'll start briefly discussing 1,3 dienes. So, conjugated molecules. Molecules possess conjugation if they have overlapping p orbitals on 3 or more adjacent atoms. So a common example of a conjugated molecule is a 1,3 diene. Okay, so we see here a 1,3 diene. We have all 4 of the carbons in this 1,3 butadiene are sp2 hybridized carbons. So each of these carbons has a p orbital. And we'll go ahead and draw out those p orbitals. Let's draw the skeleton the same way as I did over here, but let's draw the p orbitals in. Okay. So each of these carbons owns a single electron that would be in that p orbital, and then these p orbitals are overlapping to form one pi bond. And then these p orbitals overlap to form the other pi bond. And there's a sigma bond connecting carbon 2 and carbon 3 in this molecule. But because these p orbitals are all adjacent, the pi electrons are delocalized. Even though there's a sigma bond connecting the 2 pi bonds, we have a total of 4 pi electrons here. And those 4 pi electrons are delocalized due to that overlap or that conjugation. And as we learned in Chem 351, anytime we can delocalize electrons, we're going to lower their energy and we're going to stabilize the system due to that lower energy. And so conjugation provides a stabilizing effect, and we'll show that in a few different ways. The first thing we'll do here is look at an electrostatic potential map. So let's take a look at this figure from the book showing 1,3 butadiene, which is a conjugated diene, and 1,4 pentadiene, which is an isolated diene or a non-conjugated diene. And so what we see here, remember that on electrostatic potential maps, red means negative and blue means positive. Very, very easy for BYU students to understand. But we see here the red region is spread out over those 4 carbons, indicating the delocalization of the electron density of those pi electrons. But in 1,4 pentadiene, what we have is an sp3 carbon in between our 2 pi bonds. Okay, so we have an sp3 carbon interrupting those 2 pi bonds, and we end up with an isolated diene where we have 2 separate regions of electron density, 2 separate areas of red, as opposed to having just one red region. And as we'll learn later on in our next lecture, conjugation stabilizes or lowers the energy of a molecule because we're delocalizing those pi electrons. Okay? So another type of conjugated system is the allylic carbocation. So the allylic carbocation, we learned the term allylic last semester. It refers to something that is adjacent to a double bond. And so if we have a carbocation adjacent to a double bond, that's going to look like this. We know that carbocations are sp2 hybridized, so we have a p orbital on this carbon. So if we draw the p orbitals of our allylic carbocation, they'll look like this. And when we draw it this way, we're going to put a little bracket here in the upper right corner and a positive charge there, indicating that this species is a cation. Okay? So here we have 3 carbons, each of which has overlapping p orbitals because they're adjacent, 3 adjacent sp2 hybridized carbons with p orbitals. In this case, we only have 2 pi electrons, but those 2 pi electrons are spread out or delocalized across these 3 carbons. Okay? And so the allylic carbocation is a conjugated system because it has overlapping p orbitals on 3 adjacent atoms, 2 pi electrons spread out over 3 carbons, as opposed to our diene where we had 4 pi electrons spread out over 4 atoms. But in both cases, we have delocalization of the pi electrons due to conjugation, and that provides stability. We can also show the delocalization of the pi electrons in the allylic carbocation by resonance. We can draw another resonance structure of this allylic carbocation. Whoops. It looks like this. Okay. So we have 2 resonance structures that are equivalent in energy. And so that tells us that we have the maximum degree of stabilization due to resonance. Whenever those resonance structures are equivalent, that gives us the most amount of stability due to resonance that is possible. And of course, we could draw a hybrid structure, and that hybrid structure would have dashed bonds like this. And we would have partial positive charges on each carbon, each of the terminal carbons of this allylic system. We could even write +1/2 if we wanted to, because the +1 charge of that allylic carbocation is shared equally by these 2 carbons. So each of those carbons has a 1/2 charge. Okay. So you'll notice that in these individual resonance structures, these are primary carbocations. And we told you in Chem 351M that primary carbocations are too high in energy to exist. Okay? But a primary allylic carbocation, because of the resonance stabilization, is stable enough to exist. In fact, this simple allylic carbocation is roughly comparable in energy to a normal secondary carbocation because of that resonance stabilization. Even though the positive charge is on primary carbons, because that positive charge is spread out or delocalized due to conjugation, due to resonance, that allylic carbocation is comparable in energy to a secondary carbocation. And we can see that by looking at some electrostatic potential maps. So here we have a hypothetical primary carbocation, a localized or non-delocalized carbocation, and we see an intense blue region concentrated on a single atom, indicating that that positive charge is localized to 1 carbon. Whereas in the simple allyl carbocation, we see that that positive charge is spread out over both of the terminal carbons. And we see less intense blue, indicative of lower charge, lower positive charge, and we see it spread out over the 2 carbons. Another indication of the delocalization of the positive charge due to conjugation can be seen by NMR spectroscopy. So remember, we learned about shielding and deshielding and its impact on chemical shift. A positively charged carbon is going to be very deshielded. It is electron deficient, so it will be very deshielded. Accordingly, you would expect an incredibly high chemical shift for a positively charged carbon. And indeed, this tertiary carbocation, you can take an NMR of this species. Of course, it doesn't exist by itself. It has to have an anion counterion somewhere. But if you take an NMR of this compound, you find that that positively charged carbon is very deshielded and shows up very far downfield, way off the typical scale of C13 NMR. But then here we have this allylic carbocation, this resonance stabilized carbocation or conjugated carbocation, we see it's still deshielded. 224 is pretty high for chemical shift, but much less deshielded than the non-delocalized carbocation. I should note, calling this localized is not entirely correct. Remember, we learned that the positive charge in carbocations can be delocalized due to hyperconjugation or due to inductive effects. But the delocalization due to hyperconjugation or inductive effects is much less than the delocalization due to the resonance that we get when we have conjugation. Okay, so there's only very small amounts of delocalization due to hyperconjugation and inductive effects here, much larger amounts of delocalization due to the resonance or the conjugation. Okay, so now let's review the topic of resonance. This is something that we learned way back in chapter 1. We've revisited it throughout Chem 351. It's going to be vital to us in these next few chapters, so we need to make sure that we have a good understanding of the topic of resonance. So let's look at common types of resonance, common systems that will exhibit resonance. Okay, there are a few of them that we should be able to recognize. The first one is one that we've already drawn on the board, and that is the allyl system. Whenever we have a cation, an anion, or a radical adjacent to a double bond, we have an allyl system, and we have resonance. And we can draw that in this fashion, just using X, Y, and Z as generic letters. These can be carbons, they can be nitrogens, they can be oxygens. So we'll just use X, Y, and Z. And I put an asterisk on Z. That would mean that Z is either an anion, a cation, or a radical. And with the allylic system, we can draw another resonance structure where we transpose the position of the double bond and the anion, cation, or radical. Okay? And we learned about allylic radicals in chapter 15, our last chapter. Hopefully you remember back before Christmas when we were learning about radicals. Examples of an allylic carbocation, we've already shown you one, but I'll go ahead and draw another one for you. Right, this allylic carbocation has a resonance structure. It's a resonance structure that is equivalent, right? So that we have the positive charge shared equally by each of these two carbons. We have a bond order of 1.5 for each of these carbon-carbon bonds in this particular case. We've also seen allylic anions before. Back in chapter 2 when we learned about acid-base chemistry and we learned about resonance stabilization of conjugate bases, we learned about the acetate ion, the conjugate base of acetic acid, and we have a resonance structure that we can draw. So acetate is an example of an allylic anion. And here's our resonance structure. Again, these are equivalent. The negative charge is shared equally by these two oxygens. Okay, so allylic cation, allylic anion. You saw allylic radicals in our last chapter, chapter 15. Okay? All right, so let's look at another type of resonance. We'll just raise that up a little bit. And that is conjugated double bonds. So we know what conjugation means. That's where we have just a single carbon-carbon sigma bond connecting two or more double bonds. And we've seen examples of that. We've seen the 1,3-diene. We have that up here on the top of the board. We can have cyclic systems with conjugated double bonds. We're going to study that in our next chapter, chapter 17, when we study benzene and aromaticity. So this is a Lewis structure for benzene. And you see that it is conjugated because in each case we just have one carbon-carbon sigma bond connecting the double bonds to each other. And all of the carbons are sp2 hybridized. There's no sp3 hybridized carbon. When we have a cyclic conjugated system, we can draw a second resonance structure by moving the pi electrons like this. Okay. And these structures are equivalent to each other. And so the true structure, as we will discuss in chapter 17, the true structure of benzene is a hybrid of these two structures with equivalent bond lengths between each of the carbons as opposed to alternating double and single bonds. Okay. In the case of the acyclic system, we'll need to raise the board here and draw that on the lower board. We can draw resonance structures when we have acyclic conjugated double bonds, but those resonance structures are a little different than when we have the cyclic conjugated double bonds, in that we have a major contributor and minor contributors. Okay, so here's our simplest 1,3-diene or conjugated diene, acyclic diene, 1,3-butadiene. And what we can do is we can move the position of the pi electrons like so. And so what that does is it gives us a resonance structure where we have a carbon-carbon double bond between carbons 2 and carbon 3. And then we have a negatively charged carbon here on the right, positively charged carbon on the left. We could also have those pi electrons go the other direction. I'll show that with dashed arrows. And that would give us a second minor contributor where we would have the positive charge on the right, the negative charge on the left. Okay? Obviously, these resonance structures I've drawn on either end are minor contributors. They're significantly higher in energy than the one I've shown in the middle because they have fewer bonds and more charges. Even though they're minor contributors, they do contribute some to the overall structure of the 1,3-diene, and that's something we'll talk about a little more in our next lecture. Okay? So we have resonance with acyclic conjugated double bonds, but it's different from the resonance that we have when we have cyclic conjugated double bonds. These cyclic systems are special, and we'll talk about that in chapter 17. Okay? A third type of system where we have resonance is when we have a cation adjacent to a lone pair, or usually it's more, sometimes it's more than one lone pair, but it's only one lone pair that participates in the resonance. So if we have a molecule like this, there's at least one lone pair on X, so that's either going to be an oxygen, a nitrogen, or a halogen in most cases. We have a positive charge on Y. Then we can convert the lone pair into a pi bond. And then what that does is move the positive charge from Y to X. Okay? So a prime example of that would be this type of species. Okay, this should look bad. This should make you cringe because I've drawn a primary carbocation here. but it's not really a primary carbocation. It's a resonance stabilized cation where we can draw this second structure where we now have the positive charge on the oxygen. Okay? Hopefully you're wondering which of these two structures is the major contributor. It's the one on the right. Sometimes students get tripped up and they say, oh, oxygen is more electronegative than carbon, so I don't want a positive charge on oxygen. I'd rather have it on carbon. That's not accurate in this case because what we have is a situation where the resonance structure on the left has a carbon that does not have the octet. This carbon only has 6 electrons, whereas in the resonance structure on the right, all of the atoms, other than the hydrogens, of course, but all of the non-hydrogen atoms here have satisfied octets. So when we have this type of resonance, where we have a cation adjacent to a lone pair or lone pairs, the resonance structure that has the double bond is going to be the major contributor because all of the octets are going to be satisfied of all of those atoms. Okay? All right. And then the last type of structure where we have the ability to draw resonance structures in terms of a common structure where we have resonance is when we have double bonds with one atom more electronegative than the other. Okay? So two different atoms of differing electronegativities. So XY would be that scenario. And let's say that Y is more electronegative than X. Y is going to be pulling on the electrons, those pi electrons, more strongly than X will. And we can represent that in terms of resonance by drawing a resonance structure that looks like this, where we would have a lone pair and a negative charge on Y, an empty p orbital and a positive charge on X. So what's a practical example of that? Let's draw that over here. A carbonyl compound, such as a ketone. This is acetone, our simplest ketone. We'll go ahead and draw the lone pairs in on oxygen. Oxygen is more electronegative than carbon. And so we can draw a second resonance structure where we move the pi electrons onto the oxygen. And we end up with a structure looking like this. Okay? Now, hopefully you recognize that the structure on the left is our major contributor. The structure on the right is our minor contributor. We have more bonds and fewer charges on the left. So why do we care about this minor contributor? Well, it's important because what we'll learn throughout the semester is that minor contributors often provide clues about the reactivity of a molecule. This minor contributor tells us that acetone should be nucleophilic or Lewis basic on oxygen and electrophilic or Lewis acidic on carbon. And we will see time and time again when we study the chemistry of carbonyl compounds, which will take up about a third of the semester, we will time and time again see nucleophiles attacking that electrophilic carbon. We will also frequently see acids, either Bronsted acids or Lewis acids, protonating or complexing to the Lewis basic oxygen. Okay? So this minor contributor shows us a lot about the reactivity of acetone, even though it is a minor contributor. So let's take a look at some sample. This is a sample problem from the book. Some species where we're drawing different resonance structures. And here you see that we have an allylic system. And when we draw this resonance structure, we end up with a second allylic system. So what we have here is a case where the positive charge is shared by 3 carbons. Down here, we have the case where we have a double bond between atoms of differing electronegativity. So that allows us to draw resonance structure E. And lo and behold, what that does is it gives us now an allyl unit. And so now we can draw a third resonance structure of this particular compound, okay? So these sample problems show you that sometimes you end up with more than one of these features, and that allows you to draw multiple resonance structures for a given species. The one we see here at the bottom in B is going to be significant. What we see is that this is a conjugated system, right? This has a carbon-carbon double bond conjugated to a carbon-oxygen double bond. So we have 4 pi electrons delocalized over 4 carbons. This molecule is stabilized by conjugation. And we also see, because of this minor contributor, this has 2 minor contributors and 1 major contributor. And in the second minor contributor, we see a positive charge on this particular carbon. When we get to chapter 24, we will see that this molecule is electrophilic at this carbon, and we can predict that based on this minor contributor. So understanding resonance is very important. Understanding the structures of minor contributors is going to allow us to understand the reactivity of many different species that we will encounter this semester. Okay? So as we looked at some of these structures, we identified major and minor contributors. So we need to go over some rules for doing that to make sure that we're all on the same page. And we'll come over and do that over here on this sideboard. So these are rules for evaluating the relative stability of resonance structures. And these are rules that we learned back in chapter 1. We may not have phrased them in exactly the same way we'll phrase them now, but we did learn them back in chapter 1. So the first one, I've alluded to it a couple of times with these examples we've gone over. Resonance structures with more bonds and fewer charges are more stable. Okay? And a prime example of that is this example number 4 that we have here on the board with our acetone. We have more bonds and fewer charges in our structure on the left, and so that is more stable. That is the major contributor. The structure on the right is the minor contributor. Okay? Our second rule that we'll go over, resonance structures that obey the octet rule are more stable. So if all of the atoms in a resonance structure have the octet, then that structure is going to be more stable than one in which one or more atoms does not have a satisfied octet. And our example of that is number 3 here on the board, where the structure on the left, the carbon does not have a satisfied octet. The structure on the right, all of the atoms have a satisfied octet, so the structure on the right is the major contributor. So there's more of a positive charge on oxygen than on carbon. This is a large partial positive charge, close to 1. This is a small partial positive charge, close to 0 in the hybrid structure. Okay? And then our third one, we don't have an example of on the board yet, but it is one that we learned earlier, and it is one that we need to understand, and we will be applying it in other scenarios during the semester. Resonance structures with the negative charge on the more electronegative atom are more stable. Okay, and like I said, we don't have an example of that on the board, so I'll draw one. Okay, this is the conjugate base of acetone. If we deprotonate one of these carbons, we end up with a species looking like this. And this is an allylic anion. So we can draw a resonance structure. Okay. We can't distinguish between these resonance structures based on either rule number 1 or number 2. We've got the same number of bonds and charges in both cases. All the atoms have satisfied octets, but the structure on the right is more stable than the structure on the left because the negative charge is on an oxygen on the right, whereas the negative charge is on a carbon on the left. So if we have the negative charge on the more electronegative atom, that's going to be more stable and will be the major contributor. So this resonance stabilized species, which is known as an enolate, a species you'll become very familiar with later on in the semester, the major contributor of the enolate has the negative charge on oxygen. So you have a partial positive charge closer to 1 on the oxygen, a partial positive charge closer to 0 on the carbon. Okay? Please note that the corollary to this rule is not valid. You cannot say that putting the positive charge on the less electronegative atom leads to a more stable structure. If that were so, then with example 3, we'd say the structure on the left is lower in energy than the structure on the right. That's not the case. With positive charges, it's typically the octet that tells us which structure is the major contributor. With negative charges or anions, it's putting that negative charge on the more electronegative atom that tells us which is more stable. All right, the last couple minutes here, let's talk a little more about conjugated dienes or 1,3 dienes. Okay, so first of all, if we have substituents on the ends of our 1,3 diene system, we end up with a situation where we can have stereoisomers. Remember, we have cis and trans isomers of alkenes, or E and Z isomers, depending on the nomenclature that you're using. And when we have a 1,3 diene, there's 3 possible stereoisomers that we can have. And we'll just use R to represent the substituents. Okay. So here, both of our double bonds are trans. So we could call this the trans-trans isomer. Or, remember, we also learned other nomenclature, E and Z nomenclature. This would be EE. Okay. Both of those double bonds are E. We could have a situation where both of the double bonds are cis or Z. So this would be cis-cis or ZZ. Or we could have a cis and a trans double bond. That would look like this. Okay, cis-trans or ZE. Okay. So there's 3 different types of stereoisomers that you can have with 1,3 dienes. If these R's are non-hydrogens, okay, if these are alkyl groups, then you end up satisfying the criteria for having cis-trans or EZ isomers in your dienes. Now, in a 1,3 diene, we have a single bond connecting our 2 double bonds. And we have free rotation about that single bond. Okay? We cannot rotate, of course, about the double bonds. We know that if we were to do that, the pi bond would break. So we don't have rotation about the carbon-carbon double bonds, but we can rotate about the carbon-carbon single bonds. Okay? So that means that we would have an infinite number of conformations due to the rotation about the carbon-carbon single bond. However, 2 of those conformations are significantly lower in energy than all the rest. And that's because all 4 of the carbons in our diene have to be coplanar. They have to be in the same plane in order for the molecule to be conjugated. They all have to be in the same plane in order for those p orbitals to overlap with each other, to gain the stabilization from conjugation, we have to have those atoms planar. So the planar conformations are going to be more stable. They're going to be lower in energy than the non-planar conformations. And there are two of these planar conformations, and we'll illustrate them with 1,3-butadiene. Okay? So we could have the ends of our diene systems pointing towards each other. Okay? And we refer to this as S-cis. Cis means on the same side. S means single bond. Okay? So if we're looking at the single bond, and we see that our two double bonds are on the same side of that single bond, these are all in the same plane, and so the double bonds are on the same side of that of the single bond, we call that S-cis. Okay? Of course, we can rotate about that single bond, and we can end up with, I guess I have to draw these arrows because it's an equilibrium between two conformations. We can end up with a structure where the two double bonds are on opposite sides of the single bond. And as you might guess, that is referred to as S-trans. Okay? So in both of these conformations, all four of our sp2 carbons are coplanar. They're all in the same plane. So these are both conjugated. They're both low energy conformations. In this case, the double bonds are on the same side of that single bond. In this case, they're on opposite sides. So S-cis versus S-trans. Important nomenclature for us to understand. Okay? Hopefully you're wondering which of these is lower. They're both low energy conformations, but one is lower in energy than the other. You might recognize that the S-trans conformation has less steric hindrance than the S-cis conformation. Here you're going to have these hydrogens pointing towards each other, and you'll have some steric hindrance or steric strain that you don't have in the S-cis. Okay, we'll stop there for today. We'll continue on discussing dienes and reactions of dienes in our next lecture.